Okay, so in this video, I would like to prove that if G is an abelian group, and if the order of G is odd, then the product of all the elements of G has to equal the identity. So initially, this might seem like a confusing statement, and it might be hard to know exactly where to get started. But it is easier if we think a little bit more about the elements of G. So proof, the first thing that we want to think about is the elements that are contained in G. And we know that G contains at least the identity. And other than this, maybe G is cyclic. So maybe the remaining elements are just powers of A for some A and G. So we don't really know exactly, but we know that this contains A1, A2, down to some AK. And what we know is that all of these elements of G have an inverse. So we know that if we take, for example, A1, something in this group is the inverse of A1 besides the identity, possibly A1 itself. But we run into some trouble if A1 is the inverse of A1. So A1 inverse equals A1. And this actually gives us a problem because if we think about powers of A1, A1 and then A1 squared, well, A1 squared is actually the same as A1 times A1. And this has to be the identity. But we know that in any group, the order of an element of the group has to divide the order of the group. So in particular, we know that this can't happen. So this can't happen. Because in this case, if A1 squared is the identity, then that means that the order of A1 is equal to 2. And 2 can't divide the order of G because the order of G is odd. So what we know is that for all of these non-identity elements, for A1, A2, down to AK, all of these elements have an inverse other than themselves. And so what we can do is we can actually pair these off. So we know that for every AI, there's a distinct element AJ that's its inverse. And so we can actually divide these elements into pairs. So we have A1, A1 inverse, and then we have A2, A2 inverse. This is assuming A2 isn't the inverse of A1. And we know that we can divide all of these remaining elements into pairs. And there's an even number of these elements, right? Because the total number of elements in G is odd. So if we look at the elements besides the identity, so the order of G minus the identity, then this has to be even. So we can pair all of the elements of G off with each other besides the identity. And we compare each element with its own inverse. And so now if you think about multiplying all of the elements together, create some room here. So if you multiply all the elements together, you're going to have, first of all, E. But then you're going to have A1, and you're going to have the inverse of A1. You'll have A2. You'll have the inverse of A2. And then all the way down, you have AK and the inverse of AK. And all of these just become the identity. So this becomes the identity. This becomes the identity, and so on. And so that means that the product of all of these things is just the product of the identity, which is E. And it doesn't really matter what order we do this in because G is abelian. So that's it.